Hello everyone and welcome to Mathematics Tutorial 8, the third in our Powers series. Today I would like to introduce the concept of linearization, and we're largely talking about manipulating data here, playing around with data in order to yield a linear relationship between our data set. In particular, this is important when we have a curved graph and we wish to linearize it. Now, the first question is, why bother to linearize at all? And this is an important aspect in chemistry. If we get results from a laboratory whereby the relationship between the variables that we've studied isn't necessarily obvious, it may appear as a curved line. That doesn't necessarily mean that there's not a straightforward relationship between the variables under study, and coupled with that, it can be rather difficult to attain or ascertain the equation of a curved line. So one of the simplest and most powerful ways to replot data is to replot it in such a way that a straight line is formed, and we are easily therefore able to ascertain the form of that straight line, and we call this process linearization. And this is particularly important for reaction kinetics that you will all study in your first year. So by means of a worked example then, this equation here is the linear form of the Gibbs-Helmholtz equation, and look, straight away we see that this is the linear form of the equation. T in that equation is the thermodynamic temperature, delta H is the change in enthalpy, and delta G is the standard change in the Gibbs function, while C is a constant. Don't worry about the equation. It's not important that we understand the parameters in the equation. It's important that we look at the form here. Here is some data which relate to the reaction of ammonia and oxygen, and we're given a value for temperature and a value for the change in Gibbs energy. So this is the raw data that we obtain from the laboratory. So I'd like to head over to Excel now and take a look at this data in a little bit more detail. Okay, so we are in Microsoft Excel now, and that exact data that I showed you on the PowerPoint slide is in front of us. Let's plot the data up with temperature as our x-axis, because that's the variable we are changing, and the change in Gibbs energy as our y-axis, as that's our dependent variable. So I'll plot a scatter plot. And the first thing you notice about that graph is that this is not a straightforward linear relationship between temperature and the change in Gibbs energy. So I'm going to delete that graph, and let's have a look at the equation again in a little bit more detail. So you can see that that graph of delta G against T is not linear, but importantly, that doesn't mean that there's no relationship between the two. And we can read that linear form of the Gibbs-Helmholtz equation, which was cited in the PowerPoint slide before we moved into Excel. And when we do that, we can compare it to the y equals mx plus c, the equation of a straight line. And you'll notice that the linear form of the Gibbs-Helmholtz equation takes the form of a equation of a straight line. So the delta G over T parameter you see there is y. The delta H parameter is m, your gradient. The 1 over T parameter is x, and C is your intercept. If I now start to plot that up, so if I look at the linear form of the Gibbs-Helmholtz equation, and I plot delta G over T by 1 over T, let's see what happens. So 1 over the temperature, so I can do that calculation, equals my temperature, equals 1 divided by my temperature, versus delta G over T, so equals that divided by my temperature. And when I plot that, I'm instantly greeted with a straight line. And I can use Excel then to calculate the equation of that straight line, and I can learn some interesting things. I can very easily determine the value of this constant C, which is equal to my intercept. I can very easily determine the change in enthalpy for that reaction, which will be the gradient of this graph here. So by linearizing the data, I've made it much more easy to ascertain things that I'm interested in. Now, of course, we are interested in linearizing curved graphs then, and often we don't know the exact mathematical form that the graph should take, and we've got to determine the nature of that relationship for ourselves. Most relationships that involve indices will follow one of two forms. That can be y equals ax to the power of b, or y equals abx. X then is the variable that we're controlling, and y is the observed variable, and a and b here are constants. So when you obtain data in the laboratory, it's very common to obtain data in chemistry that clearly follow one of these relationships that involves indices. But we don't necessarily know the values of A and B. So what we can do is manipulate the data in such a way that the graphs become linear in much the same way as I showed you on the previous few slides. We can linearize the data, which makes it much more easy to obtain the equation for the straight line, and in doing so we can very easily calculate values for A and B. So look at this relationship here, y equals ax b. X is our control variable and y is our observed variable. In order to linearize this equation, linearize data that follows this form, we first take its logarithm. So ln y is equal to ln a plus ln xb. And we end up in this form because of one of those laws of logarithms that we looked at in the previous lecture. Now we can rewrite that equation slightly due to the third law of logarithms, and that comes out as ln y equals ln a plus b ln x. And this then is the equation that we're interested in. This is what's going to linearize our data. If you look at that equation, it has a clear resemblance to the equation of a straight line. That ln y parameter is your y-axis, the ln a parameter is your intercept, b here is your gradient, and ln x is your x value. So if we plot a graph of ln y against ln x, we can expect to get a straight line. The gradient of that line is equal to b, and the intercept is equal to, in this case, ln a. So we can very easily calculate the value of our intercept as of our parameter a here as the exponential of the intercept. Let's have a look at a little worked example here. In an adsorption experiment, ethanoic acid in water adsorbs weakly to the surface of alumina. the mass of adsorbed ethanoic acid is related to its concentration at equilibrium C, C being the concentration here. The data follows the Freundlich isotherm, which is this equation here, m equals kc to the power of 1 over n. M here is the mass of substance adsorbed on the alumina, and C is the equilibrium concentration of the substance absorbed. K and N then are empirical constants, and we're asked by means of a suitable graph to determine the values of K and N. And you'll note that that Freundlich adsorption isotherm takes on the form of one of those indice equations that we were looking at a couple of slides ago. It takes on that y equals ax to the power of b form. Now, if I simply plot mass versus concentration, you can see that I don't yield a straight line. And we noted on the previous slide that Freundlich adsorption isotherm equation obeys the form y equals axb. And if I take the natural logarithm of that equation, then I yield the following equation. And I can rearrange that slightly based on my knowledge of the laws of logarithms and obtain an equation which now resembles that of a straight line. So this is the equation that I'm after, where I will plot ln m as my y-axis, ln c as my x-axis, and therefore the gradient will be equal to 1 over n, and the intercept will be equal to the natural logarithm of k. When I do that, you can see that I obtain a lovely straight line, and I can describe that straight line by an equation for the straight line, and you can see that on the graph there. Let's have a look at that equation which describes the straight line. We're trying to work out a value of n. We know that 1 over n is equal to the gradient here, and I can see the gradient on the equation for the straight line. So I know that 1 over n is equal to 0.47, and a very simple rearrangement tells me the value of n is equal to 2.13. Similarly, I'm trying to work out a value for k here, and I know that the value of my intercept is the natural logarithm of k. So I know that k is equal to the exponential of minus 6.26, and when I calculate that, I get a value for k as 1.91 times 10 to the minus 3, i.e. the equation of the line describing the mass of ethanoic acid adsorbing onto alumina as a function of concentration can be described through that equation there. Now, what I've done this week is, because a lot of these concepts involve you playing around with data, I have put some questions onto the Moodle space associated with this mathematics tutorial, and I'd like you to have a go at some of these linearizations yourselves. And what I've also done is I've put up a spreadsheet where you can check to see if you've got the right answers. So I've gone through the exercises myself as well and plotted the graphs up and calculated the values, and you can double check by looking at the spreadsheet and follow my processes as well. Thank you very much.